Hey everyone, welcome back to Education is Life, your go-to channel for unlocking the wonders of learning. It is me, Joe Edgo, and today we're on Lesson 12 of the Arduino UNO R4 Ultimate Training Series, focusing on implementing non-blocking code using millis. For today's lesson, you'll understand why using millis instead of delay is the proper way to implement timing events in your Arduino code. You'll learn how to properly branch your code using many different references to time in order to perform several tasks simultaneously. This means that you can create projects involving several components without blocking each other's time of execution. At the end of this lesson, you'll be controlling a servo motor while performing a traffic light operation and still be able to receive a signal from a sensor without having to wait for the previous task to complete before performing succeeding task. As always, before we start, I'd like to extend my sincere gratitude to SunFounder for sponsoring this course and enabling everyone, especially beginners, to embark on this comprehensive educational adventure. Throughout this series, I'll be using this amazing SunFounder Arduino UNO R4 Minima Ultimate Sensor Kit. This kit is packed with everything you need to build amazing Arduino IoT projects. So, if you're still looking for a learning kit, I encourage you to please check this one out. This is available on the SunFounder website as well as on Amazon. The links are provided below. So now, let's begin. For this session, you need the following materials: an SG90 micro servo motor, a normally open momentary push button switch or the SunFounder button module, 3 LEDs with 3 current limiting resistors, or simply the SunFounder traffic light module, and of course, a breadboard, some connecting wires in your Arduino UNO R4 Minima. In most of our previous lessons, we usually call the delay function to accomplish various tasks like making an LED blink at a certain frequency or positioning a servo motor at a certain angle at a specified speed. Well, using the delay function is actually good if you intend to pause the execution of your Arduino program for a specified period of time. And there are some suitable applications as to why you would want to pause your program execution for a certain period, like when performing sensor initialization, or perhaps your program needs to pause for a while due to human interaction. However, you need to understand that the delay function is a blocking function that prevents your Arduino program from doing anything else until the specified time has elapsed. So, if you have several lines of code and you have delay function calls somewhere in between these codes, the succeeding code execution will be put on hold until the delay is finished. So, what's wrong with that? Well, the problem arises when your program needs to perform multiple tasks or events at the same time. You simply cannot do that using the delay function. Now, just a reminder, since I mentioned multiple tasks, some of our advanced viewers here, especially programmers, might compare this topic on how multitasking is done in their computer's operating system. Please bear in mind that Arduino UNO R4 is not similar to your desktop computer or your smartphone, which allow running multiple programs on top of an operating system. However, there is a way we can run operating system on your Arduino UNO to support multitasking, and this is called RTOS, or Real-Time Operating System. But still, technically, RTOS simply creates an illusion of multitasking by executing parallel instructions one at a time. For now, we're not going to discuss that. So just to make things clear, we're not going to run multiple programs at the same time. However, although we can only run one program at a time, that doesn't mean we can't manage multiple tasks. Tasks like blinking an LED, reading sensor data, controlling motors, and others. In Arduino, we just need to change our perspective on doing things. Since we're not going to use an operating system to help us, we have to do things ourselves through our code. We're going to write non-blocking codes to handle several tasks simultaneously, creating an illusion of multitasking, making our program stay responsive. To illustrate this concept, let's hook up this simple circuit diagram. Here, we have the green, yellow, and red LEDs connected to pins 5, 6, and 7 respectively. Then an SG90 servo motor signal wire is connected to pin 9. And finally, a button module is connected to pin 2. If you want to refresh your memory on how these components work, please check the links to the previous lessons below. Let's start the concept by creating a simple blinking LED program. Say we'll make this yellow LED blink at an interval of 250 milliseconds. So to do that, I'll define yellow LED at pin 6 and then set its mode as output. And finally, in the loop function, I'll turn it on, delay for 250 milliseconds, and then turn it off, and then another delay of 250 milliseconds before looping back to repeat the process. And we know that this is going to work because we've done this a dozen times. Now, to illustrate the point of why we don't use blocking functions, like this delay function call, when we try to perform many different things simultaneously, let's also control the servo motor at the same time. When I say at the same time, let's make a program that positions the servo motor from 0 degrees up to 180 degrees, say at a speed of 15 milliseconds per degree, while the yellow LED is blinking at an interval of 250 milliseconds. So, one LED blink, meaning one on-off cycle, will consume 500 milliseconds. And for the servo motor, 15 milliseconds per degree for 180 degrees gives us 2,700 milliseconds. That's roughly about 5.5 LED blinks for the servo motor to position from 0 to 180 degrees. Well, this can only happen if both tasks are going to be executed at the same time. However, with this current code structure, it is not possible. To show you, first, let's include the Servo library, or you can use the PWMServo Library for a much smoother shaft movement. Please refer to the previous lesson on controlling servo motors. However, please note that when using this PWMServo Library, make sure to check if the version of your Arduino UNO R4 boards installed is version 1.0.5. It will not work with the recent update of version 1.1.0. Then, I'll define the servo motor pin at pin 9, and then create an object of this servo I'll call servo1. In the setup function, I'll attach the servo pin to the servo object, and then set the initial position of the servo motor at 0 degrees. Finally, I'll just put a 1-second delay before the loop starts. Now, inside the loop function, just after this delay function call, I'll create a for loop to position the servo motor from 0 to 180 degrees, incrementing 1 degree every 15 millisecond delay. So, I'll upload this code and see what happens. As you noticed, it only blinks once and then followed by a servo motor rotating from 0 to 180 degrees, and then the process repeats. However, this is not what we want. The two tasks, the blinking LED and the servo motor rotation, do not execute in parallel but rather in sequence. This is because we're using the delay function call all over the place. During program execution, the delay function literally blocks the succeeding codes from executing until the specified time delay is finished. So to illustrate how to write non-blocking codes, I'll delete this entire code and let's just focus on a single task in the meantime, the blinking LED. We'll write a program to make this LED blink at a certain interval without using any delay function call. And to do that, we need to understand how millis function works. The millis function returns the number of milliseconds that have passed since the Arduino board began running the current program. So essentially, it is a timer for how long the current program has been running. The return type of the millis function is unsigned long. So I'll create a variable I'll call current time and store the return value of this millis function call. And then let's print this value to our serial monitor. Of course, we need to set up this serial communication first. Now, let's upload the code and see what happens. As you can see, these are the number of milliseconds that have passed since the program began running. Please note that this is independent of the number of times the void loop has iterated. So, how long can it count? Well, technically, since the return type of this function is unsigned long, which is 4 bytes, that's 32 bits, it means that it can store numbers from 0 up to 4,294,967,295. And if each count is roughly 1 millisecond long, then it will take almost 50 days before this variable overflows, meaning almost 50 days before the 32-bit container resets to 0. Now, the question is, how can we make use of this millis function that continuously returns the number of milliseconds that have passed since the program began running? The answer is that we can make use of these values to check how long a certain portion of our code has been running. For example, if the code that turns on the LED starts at about 1000 milliseconds, and what we want is to turn it off after 250 milliseconds, then we can keep on reading this return millis value and check if 250 milliseconds have already passed. And if so, we can execute the code to turn off the LED. So, how do we check if 250 milliseconds have passed? Well, simply subtract the start time when the code that turns on the LED is executed, which is 1000 milliseconds, from the current time, and then check if it is already greater than or equal to 250 milliseconds, which is the time elapsed. If this condition turns true, then we know that 250 milliseconds have passed. So, it is time to execute the next code, which is to turn off the LED. Now, using the same approach, we need to mark this current time as the new start time when the LED is turned off. We need to do this so that we can use the same condition to check if another 250 milliseconds have passed so that we can turn on the LED again. And then, mark this current time as the new start time, and the process repeats. Let's try implementing this in our code. First, we need to declare an unsigned long variable I'll call start time. Also, I'll declare an unsigned int variable called interval. This is our elapsed time, which is 250 milliseconds. Now, before going to the loop function, I'll initialize the start time variable by getting the current milliseconds. This marks the starting time just before we turn on the LED. So, inside the loop function, I'll turn on the LED. Now, the question is, how do we turn this off after 250 milliseconds have passed? And then, turn it back on after another 250 milliseconds have passed, and so on. So, this is where the trick begins. Inside this loop function, we need to continuously get the current millis to know the current time. And then, ask if 250 milliseconds have already passed since this code was last executed. So, we enclose this code inside an if block so that it doesn't execute after every loop. It only executes when it reaches a specified interval of 250 milliseconds. To do that, we simply subtract the start time from the current time and compare if the elapsed time is already 250 milliseconds. If so, the code inside the if block gets executed, which is to turn off the LED. But how do we do that? Well, there are several ways to accomplish this, but one of the easiest ways to do this without having to declare another variable is to simply use the digital read function to read the current state of our LED pin. This should return high or low depending on the current state. And then, apply a logical NOT operator to invert the current state. That is, if the current LED state is high, it becomes low. And if for the next cycle, inverting the current LED state of low becomes high. Now, there's one thing that you must not forget. You need to set or mark the new start time, which is the current time, so that we can use the same condition to check if another 250 milliseconds have passed so that we can turn on the LED again. So, let's upload the code and see if it works. And as you can see, we were able to make the yellow LED blink at an interval of 250 milliseconds without using any delay function call. Now, this code is non-blocking, which means we can have other codes after the if block and they will be executed right away without having to wait for 250 milliseconds. So, let's try controlling the servo motor to set the position from 0 to 180 degrees at a speed of 15 milliseconds per degree, but without using any delay function call. And to do this, we need to create another set of variables to hold different time references for the servo motor operation. So, I'll duplicate these variables and change them to start time servo and interval servo, but the interval servo is only 15 milliseconds. I'll also add another variable, pause, and set it to 0. This will serve as the angle position of the servo motor that gets updated every 15 milliseconds. So, in the setup function, I'll set the initial position of the servo motor to 0 degrees. Then I'll initialize the start time servo as well. Then, just after this if block, I'll declare another unsigned long, current time servo, and get the current millis before moving the servo. Now, similar to the previous if block, I'll check whether 15 milliseconds have passed so that I can update the position of my servo, that is 1 degree from the previous position. If current time servo minus start time servo, this is the elapsed time, is greater than or equal to 15 milliseconds, which is the interval servo. If so, I'll set or mark the new start time servo, which is the current time, just before updating the new position of the servo motor. Here, I'll type ++pause, which means increment the pause value by 1 before writing to set the new servo position. Now, this code is not yet complete because if we try to simulate the value of the pause variable, it will exceed the maximum degrees of 180 after 180 loops. So, I'll create another condition here that sets the new value of the pause variable once it reaches 180 degrees. I'll set it to -1 instead of 0 because of this code, servo1 that write ++pause, which means increment first before setting the new position. So after reaching 180 degrees, the next pause value to be written after 15 milliseconds is 0. So this is fast. From 180 degrees down to 0 is only going to take 15 milliseconds. However, from 0 to 180 degrees, it is going to take 2,700 milliseconds. That's 15 milliseconds per degree. Now, let's try uploading our sketch and see what happens. So, as you can see, it works. The yellow LED continuously blinks at an interval of 250 milliseconds, while the servo motor rotates at a rate of 15 milliseconds per degree. It takes about 5.5 blinks for the servo motor to cover 0 to 180 degrees. So, by computing the time differences for each task, we can benefit from the use of non-blocking codes to have an illusion of multitasking. Here, if we want to adjust the time interval, say instead of 250 milliseconds for blink rate, I'll change it to 100 milliseconds. Also, say I want the servo motor to range only from 90 degrees up to 180 degrees at a speed of 30 milliseconds per degree. So I'll upload this code and see what happens. And as you can see, it works perfectly. Now, let's add one more component to this program, a button module. And let's say what we want is when the button is pushed, regardless of the current position of the servo motor, the servo will position to 90 degrees and the red LED turns on. Now, with this current setup, this functionality is not that hard to add. First, we define the red LED at pin 7 and the button pin at pin 2. Then, set the pin mode of the red LED to output. Set the pin mode of the button pin to input. And finally, implement a condition that checks if the button is pushed, and if so, turn on the red LED. And set the servo position to 90 degrees. Otherwise, turn off the red LED. Now, I'll upload this code and see if it works. So, the previous functionality works as before, but now, when I push this button, the red LED turns on and the servo position is reset to 90 degrees. For your challenge activity, try to improve this program to imitate a simple traffic light system with a barrier represented by a servo motor. When the servo is positioned at 90 degrees, the green LED is turned on. This will last for 10 seconds. Then, the yellow LED blinks as the servo positions to 180 degrees. This will last for about 3 seconds before turning on the red LED. After 7 seconds, the servo again repositions to 90 degrees while the red LED remains on for another 3 seconds before turning on the green LED. And the process repeats. Now, the button here acts as an emergency button for pedestrian. Once it is pushed, regardless of the current state of the traffic light, it puts the traffic light into a warning state. The warning state is when the yellow LED is blinking while the barrier positions to 180 degrees. Again, thank you so much for joining me in this lesson on implementing non-blocking codes using millis. If you found this lesson enlightening, don't forget to hit the like button, subscribe for more knowledge-packed sessions, and ring the bell to stay updated. So, keep learning, keep experimenting, and always remember, education is life. See you in our next lesson. Happy coding!